And here's a little bit of data to show it. So here's what we mean by a long, here's what we mean by slanted, and here's what we mean by a cross. So this one was printed in this direction, this one was printed in this direction, they're all printed in the same direction. So what one of my colleagues did is he took a bunch of 3D printed samples, put them on a force testing machine, and started ripping them apart. The numbers that I just gave you, this kind of puts it in a little bit of perspective. What happens when you test the different orientations? So again, let's go back to this. I printed in this direction, and now the along is the strongest, the slant is the second strongest, and across the grain is the weakest. That confirms what I just told you about that rule of thumb. And the same thing, so this is the peak load, this is the maximum force that I can take, and then when you look at the stress, how much it can bend, you have almost the exact same type of results. So it fails earlier when you go with the grain, right? If I'm trying to pull apart the layers, it fails sooner. It makes complete sense, right? You have to be careful how you orient your parts because that affects how it will perform when you're actually printing it out. The nice thing about an automated 3D printer is it reduces the cost of failure. So you can print it in a bunch of different orientations and then just test it afterwards. Okay, to give you a good summary slide, I think this is a good one. This covers the main different technologies that are out there. Powder binding is, for all intents and purposes, just a combination of inkjet and SLS. They use powder and they use a glue, which they're inkjetting, and that glue holds the powder together. So instead of melting it, you're gluing it together. So I kind of bucket them. It's a combination of the two technologies. This just gives you a good high-level overview of what type of resolution you could ever expect to achieve with the best machine. When you go to China and you buy the cheap ones, you're not going to get this. They'll tell you that it's this resolution. It's not. It tells you the type of support material. So in the powder-based processes, they put powder everywhere. The powder itself supports the object. So you don't really need to design support materials. In some cases you do with metals because you need thermal supports. You need to help get the heat out quicker. So they actually print heat sinks. But from a mechanical perspective, you don't need support material because the powder itself is the support material, which is an interesting way to think about it. But what that also means is, if I want to print a tiny thing like this, and my printer has a build volume bigger about this size, you have to put powder everywhere. You're not just putting the little bit amount that you want. So it can be a very high waste process, the powder-based things. And then when we're looking here, this tells you how you can post-process the object, and this kind of tells you what's the process limiting factor. Okay. I'm not going to touch on it, I'm not going to dig into the details. These slides are available, and I think the video is going to be available as well. I highly encourage you guys to all just check out videos on YouTube of how the different post-processing works. Because what you might want to just do is use a cheap process that gets you close enough to what you want, and then post-process it to make it look pretty. Because if you need something strong, but the fuse deposition modeling process doesn't get you the surface you want, stereolithography will never be strong enough, but you can always polish or mechanically ablate the surface of an FDM part to make it look pretty. So there's different things you can do to make the form factor look nicer from an aesthetics purpose. There's not much you can do to make something stronger after the fact. The metal technologies are a little bit different. You can do post heating and tempering and things like that, but that's just kind of down in the weeds in the metallurgy of what's going on.